Thank you very much, Dr. Kritika, for this wonderful introduction. It's really a pleasure talking to people all over the, from our fraternity. And it's really a pleasure, when anyone invites me to talk on statistical methods, because I think there's a lot to learn from each other in demystifying the concepts here. So what I'll do is I'll make just a short presentation on two or three very, very important points of both parametric and non-parametric statistics. So I'll start off with the p-values and the normal curves and all that, and then we'll go on to talk about what are the most important tests and how do we go about it. And I'll try to make it short and concise, because what I've been told is that most of our viewers here would be research scholars, so they would be knowing the background of what we are going to talk about here. So I'll share the screen. I'll share the presentation with you. If you can't see that, please let me know. I'll start parametric and non-parametric statistics, as you know, and we know these are the 9 different. I mean, if I have to break down our research process into 9 discrete steps, then this would be these 9 discrete steps. Of course, the topic selection is the most important part in a research process. But if you see the, especially the points 6, 7, and 8, that's where a lot of these statistics, even the earlier ones in 4 as well, a lot of statistics is involved, a lot of analysis is involved. So this is where we have to be very, I mean, we have to know these basics in details once we carry on, or whether it's for the purpose of examination or whether it's for the purpose of doing research itself. It's important that all these concepts are very clear for all of us. If I have to divide that into these many parts, then of course, I mean, this is also possibly known to everybody, that we start off with an initial observation, and then based on the data we refine the observation, and then we generate some kind of an initial theory, and then we generate a hypothesis. The identification of variables is very important, especially the dependent and the independent variable, which we also call as the predictor and the outcome variables. And finally, we put that data to test, and then we analyze that. So this is basically the research process in one full flow, if I can put it that way. And this is from Andy Field's wonderful book on discovering statistics with SPSS. I will not put a lot of stress on descriptive and inferential, but the descriptive statistics is also a very important part of our everyday statistical work, especially if we have to find out about the population, etc. And that's where some of the concepts of mean, the median, and the outliers must be very, very clear, because often much of these things are not clear to researchers while they go ahead, and these are like some ready-made things, but we have to understand the concepts behind that. So first of all, when we talk of parameters, we are basically talking of things like mean, median, and mode. So whenever we are talking of parameters, we are talking about mean, median, mode, and such things. The problem with mean is that it is affected by outliers, although it's a very, very important test, especially as I say, for example, if we are talking about the average income or the average age or the average IQ or whatever. These are very important descriptions to have. But at the same time, the measures are vastly affected by the outliers. If there is an outlier, then the average will be starkly affected. And I give this example very often, that say 100 of us are there at the moment watching this, and suddenly I mean, if I calculate the average income of all these 100 people, it comes out to 1 lakh rupees per month. Suddenly a very rich person, Bill Gates, walks in. He's an outlier. The average income will go up. So the outlier has a drastic effect on the mean. So that is why we go for the median very often, and we'll see that the median is important when we are talking of categorical variables and ordinal variables. So I'll discuss about that as I go along. So when we have to test hypothesis or quantify the covariation, etc., we go for inferential statistics. These are basic things known to most researchers. Very important to have a very clear knowledge about what is an independent variable, what is a dependent variable, what is a moderating variable, and what is a mediating variable. Control is for experimental statistics, and control variable is what we deal when we deal with experimental statistics. So that is probably not what we are going to talk about today, but very important to know about the independent and dependent variables. There are various ways of remembering what is independent and what is dependent, because in various experiments or in various cases or in various statistical tests, they have different roles. Independent variable is the variable that causes, if it is a cause effect relationship, it is something that causes the effect on another variable. So something which causes, something which is the predictor, is the independent variable. And the data we get out of it is the dependent variable. Say, for example, we could be studying about the effect of exercise on weight loss. So we would be changing the or will be finding out people with variable time spent on exercises. Somebody is spending 1 hour on exercise, somebody is spending 2 hours on exercise, 3 hours regularly, say for example 6 months, and then we find out the percentage of weight loss. So the exercise hours, or the hours spent on exercises, is the independent role, because that variable is supposed to cause the weight loss. So from whatever we get the data, that is known as the dependent variable. Dependent variable provides me with data. So we must remember about this thing when we talk about independent and dependent. Where do we collect data from? From the dependent variable. So that's one very simple way of remembering that. Another two variables that cause a lot of distress to many of us is about what is moderating and what is mediating, because there is a very stark difference between what is moderating and what is mediating variable. So say for example, when I told you about exercise and weight loss, so the exercise is the independent variable and weight loss is the dependent variable. There could be a moderating or a mediating variable there. Say for example, the weight loss is moderated by another variable which we have to at times take care of. That moderating variable could be gender, that moderating variable could be your prior weight, that moderating variable could be any other thing. So moderating variable, it contextualizes the dependent variable. So if there is a moderating variable present, it will have an effect on the outcome variable, or it will have an effect on the dependent variable. So as I said, say for example, gender or maybe prior weight could be a moderating variable. Mediating variable is very important and very different from what is a moderating variable. Mediating variable is one which depends on the independent variable and which causes the dependent variable. So that is a very important difference to understand between moderating and mediating variables. So if we are talking of moderating variables, we have to remember that moderating variable is one which is not dependent on either the independent or dependent, but it contextualizes the dependent variable. It causes the dependent variable to be different from what it otherwise would have been. But a mediating variable is something which is dependent. Say for example, your calorie loss or your calorie intake, that is a mediating variable often, because if you do a lot more exercise, then probably your calorie intake increases, and that has an effect on your weight loss. So the calorie intake could be a mediating variable. So very important to realize the difference between what is a moderating variable and what is a mediating variable. A lot of people confuse between these two. So important to remember the context of moderating and mediating variables. Another important thing that we must remember, I don't want to get into all the details, but it's important to understand what is standard deviation. Today we don't have time to go into the details of standard deviation. I have another video on standard deviation. It's there on my YouTube channel. So if one is interested, you can go back and have a look at that. But standard deviation depends on the variance. What is variance? Variance is how far the observation is from the mean. So standard deviation basically tells us about the variability of my data. If my data is uh, very variable, then probably I'm talking about a different kind of a situation. But if my data is very narrow, then I'm talking about a different kind of I'm talking of a different kind of standard deviation. So standard deviation depends on the variance. It depends on the sum of errors, as they say. So standard deviation is a very, very important uh, figure that we will talk about. It's a very important concept that we always have to talk about, especially when we talk of the normal curves and all that. Why am I talking about all these normal distributions and all? This has a very important effect on what is parametric and what is non-parametric. So I'll be coming on to that very quickly. So standard deviation, of course, is a very important uh, measure for us, because it can be used to standardize data. So later on, we'll see that if we divide the covariance with the standard deviations, then we get the correlation. Or when we have to find out the z score, we subtract it from the mean and we divide it by the standard deviation. So that's how we get the standard values. So standard values, of course, will not have any unit, because otherwise everything will have a unit. So when we're talking of mean, it will have a unit. If you're having the mean age, then the unit will be years. If you're having mean weight, then the unit will be kilograms. So those things have a unit, but z values, they do not have a unit. They are just a number, because we are dividing it by standard deviation. So you subtract the mean and you divide it by standard deviation, you get the z value. So z value is very, very important concept to remember. So we have spoken of three important concepts as of now: the moderating and mediating variables, and what are z values. I'm sure we understand the meaning of skewness. So if I see that this is a normal curve and this is skewed. So this is it has higher values. The frequency goes up. So this is normal and this is skewed. So this is left skewed, right skewed. We know, about all those things. I'm not going to get into the details. Why is the normal distribution important? That is very, very important for us to know, because it gives us an idea. If we have a probability density, then it tells us that 95% of the values will fall between minus 1.96 to plus 1.96 standard deviations. So that is that a very important figure. So that's why standard deviations and these z values and all these things are important. So if I have a probability curve, if we know the standard deviation, then we can say with a lot of certainty that almost 97% of the value will be between -3 and +3 standard deviations. So this is a very important value to remember, that 68% of the population will be between 1 standard deviation of the mean. So if this is the mean, then 68% of the value will be between that. If I have to talk in terms of relating it to regular our everyday life, so just think of this as maybe this is the mean height of all people. Say the mean height is 5 feet 10 inches, then you'll find that the majority of the people, 68% of the people, will be between -1 and +1 standard deviation of that mean height. So that is where the entire population will kind of gather or accumulate. Almost 95% of the population will be between +2 and -2 standard deviation. So +2 standard deviation from the mean on one side and -2 standard deviation from the mean on the other side. So that's where the 95% of the population is there. Similarly for the 99.7. So 99.7% of the population will be +3 and -3. So that is why the normal curve is such an important figure to have, or it's such an important concept to remember. Now I'm going to talk about the standard error, or why, how do we get standard error and why standard error is important. So basically, again, this figure is taken from Andy Field's fantastic book. So if we have a population mean and, we draw in samples from that population, the sample mean will be different, for our different samples. So say, for example, the population mean is 3. If I draw in 1, 2, 3, 4, 5, 6, 7, 8 samples, then all my 8 samples are having different means. So if I, this one is 3, this one is 2, 4, 1, 3, 2, 5, 4, 3, whatever. If I plot these means, this will also be in like a normal curve. And the majority will be what the population mean is. And this is the standard deviation I get, and this is the mean I get. The standard deviation of the sample means is the standard error. Standard error is the standard deviation of the sample means. We don't have to take, this can be extrapolated, but this is the concept of standard error that we must remember. Also, we have the very important central limit theorem. It states that if we have a population with mean mu and standard deviation sigma, then if you take sufficiently large random samples, then the distribution of the sample means will be approximately normally distributed, or the highest frequency will be for the population mean itself. So another important concept to remember is that of the standard error. So we started off with moderating and mediating variables. We spoke of the Z figures, or the standardized values. We again spoke of the normal curve and how standard deviation has an effect there. And now we are talking about what is the standard error. The parametric tests assume 4 different things. When we talk of parametric tests, we have to talk about 4 different underlying statistical assumptions. I'll just talk about that in a minute. Non-parametric tests, they do not rely on any distribution. They can be applied even if the parametric conditions of validity are not met. So parametric conditions are very important. The conditions of parametric tests are very important. We will always prefer parametric tests because the amount of information we get from parametric tests is very rich, and it can be applied to a lot of cases. But if those assumptions are not satisfied, then we cannot go for the parametric tests. First of all, parametric tests assume that the sample is independent. That means every unit in the sample has an equal probability of getting selected. So it does not depend on any other factor. It is normal. It is assuming assuming a normal distribution. It assumes homogeneity of variance. That the variance I spoke of, it's homogeneously spread. It is not there in certain pockets of the population, but it is spread across the population. So homogeneity of variance is a very important parametric assumption. Also, the scale has to be interval at the very least. I'm sure we understand that the various scales. We know about the nominal or the categorical scales, where we are just talking of categories. Then we have the ordinal scales, where we are talking of ranks. And then we have the interval or the ratio scales. So here we are talking about the interval or ratio scales at least. If somebody is doing SPSS, the term the SPSS uses is scale. They have nominal variables, they have ordinal variables, and they have scale variables. So when SPSS talks of scale, they're talking of either interval or ratio. So basically that's a numeric scale. This is an important assumption to remember. I'm sure we know about the hypothesis test. So I wanted to talk about hypothesis in today's program as well. So basically, there are 2 things that we must understand. What is there is something which is your research hypothesis, some premise or claim that you want to test. you want to test whether the amount of time students spend on online classes, whether it has some relation or whether it has some effect on the marks they get in their examination. So that is your research hypothesis. That is something that you have to test. If I have to test it statistically, I have to begin with a null hypothesis. And that is a very important distinction. Your research hypothesis is something else, your statistical hypothesis is something else. Because statistically we have to begin with the null hypothesis, because that is something that we can test through numbers. We cannot straightway. So there are, oftentimes we are asked in classes, I'm sure you might have had the question also, that why do we go the convoluted route? Why not straight the alternate hypothesis? Because alternative hypothesis is something that cannot be tested directly. It has to be through the route of null hypothesis. What is null hypothesis? Null hypothesis always assumes that there is no effect, that whether you do online classes or not, it has no effect on the marks you get. So whatever our research hypothesis is, we always start off with the null hypothesis, which suggests that there is no effect. Whatever effect is there is due to some sampling or it is just a measurement. So there is no effect. It is just a sampling effect. So we always start off with a null hypothesis, and we have to prove whether the null hypothesis is true or not. Again, a very important thing, the hypothesis must be falsifiable, and that is where the entire theory or the entire theory of statistics stands. If it is not falsifiable, then that is not science. Now let me give you an example. If we tell you that, okay, there is a peacock in the garden. There is a peacock in the garden just beside me. That is one statement of fact. The other fact is that there is no peacock in the garden. If I tell you that there is a peacock in the garden, there is no way you can actually falsify that, because there could be a peacock hiding somewhere and you can't find it. Just the fact that you can't find it does not mean that it is not present there. But if I give you the statement that there is no peacock in the garden, the moment you see just one, that very moment you are justifying it. That very moment you can falsify it. You will say that no, your conjecture is wrong. There is actually one peacock in the garden and you couldn't see that. So that's why we start off with a null hypothesis. And the moment we start off with a null hypothesis, we have to have a process there. I will not get into details there, but very important is to select a test statistic and to specify an alpha level. And this alpha level is very important. This alpha level is not some magic number that we just bring out, or we just bring out of somewhere and we just use that magic number to get some information out. That is an assumption that we make prior to our test. That is an assumption that we have to make, or we foreground before going with the test. So that has to be specified. I'm sure everybody remembers that alpha level of 0.05 or at times 0.01. So what the alpha level means is that we are suggesting the probability of the null hypothesis being true. So when I put an alpha level of 0.5, I am putting the probability of, as 0.05 is my limit. If the probability of the null hypothesis is more than 0.05, then we accept the null hypothesis. Then we accept it. So if we have put a 5% limit, which is 0.05. So please, we must remember the probability value as a very important indicator. It is not everything. There are too many question marks after that. So we must remember about that as well. So when we put that alpha level as 0.05 or 0.01, so if it comes as below 0.05, then we have to suggest no, because this probability is very less, we can reject the null hypothesis. So we specify an alpha level for the probability of the null hypothesis being true. What is alpha level? It's the probability of the null hypothesis being true. If it is below that 0.05 or 0.01 level, whatever level we are putting, then we will reject the null hypothesis and we will accept the alternate hypothesis. No, that there is an effect. So in the example I just gave you, if it is below those levels, then I will accept that, okay, the null hypothesis is wrong. Our alternate hypothesis is strengthened. It does not prove alternate hypothesis is true. It suggests that our alternate hypothesis gets strengthened. Important to remember the difference. So we first of all have the null hypothesis and the alternate hypotheses. We have the alpha level and the test statistics. Test statistics could be T, could be ANOVA, could be whatever. We'll discuss that in a moment's time. And then we calculate the test statistics and the inference. So we calculate the values and then we make an inference. So this is what we do in null hypothesis significance testing. There are two errors, again very important. The first error is type 1 error. The second error is the type 2 error. Please, we must make it a point to remember this very, very clearly. What is type 1 error? What is type 2 error? Very often, even seasoned researchers, they have to go back again and again to find out what is type 1 and type 2, because it can get very confusing. Type 1 means false positive. False positive means that we are rejecting the null hypothesis when the null hypothesis is in fact true. The type 2 error is false negative. That means we are accepting the null hypothesis when it must be rejected. So one is false positive, the other is false negative. In clinical research, you can understand this has very, very important dimensions. So if I have to talk in terms of COVID-19, then a false positive would mean that you are suggesting that a person is COVID-19 positive when in fact he is not a COVID-19 positive. False negative in that case could be very, very dangerous. The person is COVID-19 positive, but you are passing him off as COVID-19 negative. So as you can understand that the person might even have a fatal encounter without being given the medicines because he has been shown as negative. So false negative can have a problem as there. Even false positive can have a problem that as you can understand, we are taking that 5% limit. So there is a 5% chance that we are doing something wrong. The type 2 error is not related to type 1 error. Type 2 error is something very different. So this is what we do actually. So when we reject the null hypothesis, when the null hypothesis is wrong, that is a correct decision that we are making. We reject the null hypothesis when when the null hypothesis is in fact true. So that is a false positive. That it is null, but we are saying it is not null. That is type 1 or false positive, and this is false negative. I'm not going to get into the one-tailed and two-tailed. So that again is something that we must remember, that if you are having two-tailed, then it is slightly more stringent. There are more stringent conditions on two-tailed tests. So these are the critical values. So this is the test value I suggested. So if your Z value is more than this, or if your is less than 0.05 the probability, then the null hypothesis is rejected and the alternate hypothesis. So you are doing either of the thing. Either you are going for p values or you are going for the test statistics, as I just said 2 minutes back. So it could be your t value or z value. You are finding out that critical value. If your critical value is more than the value which you get in the tables or you get it in the list, then we reject the null hypothesis. Otherwise, we accept the null hypothesis. 2 or 3 very important things we have to remember about null hypothesis as we go on, because first of all is the statistical power. It is the ability to find out an effect. So that is why parametric tests are very important, because they have high statistical power. Even if there is a very small effect, the parametric test they can find out, or they can deduce those tests. But if it is a non-parametric test, then we might not be able to get it. So the statistical power of non-parametric tests is less. We also have to report confidence intervals and effect sizes always. Just the p-value is not enough, because if you just rely on p-value, then that is regarded as bad research. So there are problems with p-value. It is just a probability. The effect can be much less. So statistically significant does not mean that the effect is stronger. There are two different things. There is one thing about effect, the other thing is about statistical significance. So just the p-value is often not enough. We have to talk about effect sizes. In a moment's time, I'll just talk about effect sizes as I go on. So one of the parametric tests is, or one of the assumptions is about, covariance. So when there are two variables who are co-varying, that means they are co-varying in the same direction, then we say that there is a positive covariance. When they are co-varying in two different directions, then we say that there is a negative covariance. If we divide the covariance with the standard deviations, we get the correlation. If both my variables are scale variable, they are either interval or ratio, then the correlation which we have to measure is the Pearson's R. If both my values are ordinal, that means they are ranks, then I get the correlation as Spearman's rho. If both are nominal or categorical, then I get phi or lambda. The other ones are biserial, point biserial. We must remember their names at least. So when we standardize the covariance, as I said, we get the Pearson's correlation coefficient. So correlation coefficient means, as I told you at the beginning, that when we standardize anything, we do not talk of its units. It's just a number. So correlation coefficient has to lie between a number -1 and +1. So when you have the number which is very high, say for example we get a correlation of 0.9 for example, and the effect is R squared, so that would be 0.81. So I just told you about the effect size when I was talking about the p-value. So it's important to remember that when we talk of the effect size, we must talk of the values of, like R that I just spoke of. So effect size means that the variation is up to 81%. The variation in the other is up to 81% of the first one. So this is important to talk about effect sizes. Just p-value is not enough. I keep on emphasizing that, and it's been well established in all other fields. Even in communication, we must keep on emphasizing just p-value is not enough. We have to talk of confidence intervals, we have to talk of the statistical power, and we have to talk about the effect size as well. Otherwise, we would not be doing justice to our research. It needs no saying. Just by seeing, we can see that something is perfectly positively correlated. As one increases, the other increases, and this is perfectly negatively correlated. This is where there is absolutely no correlation. So we can have a distinction on what correlations are. This is the formula for correlation coefficient. I don't have to get into details, but as I just said, this variance is the square of R. So if I square R, I get the variability. Very important, correlation does not always mean causation. It can be a base, but it does not mean causation. Just because one thing is correlating with the other does not mean causation. We have to keep on emphasizing that. In our talks with journalists and others, we make it a point to remind everybody that correlation does not mean causation. This is one test we do to find out whether the difference in mean are by chance or whether they are significant. So if you have say for example male students and female students in your class, and you take their communication research marks, if you want to find out whether they are statistically different, that girls score significantly higher than the boys, then we go for the t-test, and that can be very easily done through a Microsoft Excel program as well. You don't even need an SPSS program for that. So t-test is a very good parametric test. It tells us the difference between the mean. So one is about association, this is about difference. So very, very important difference. Another important thing is that if we have more than two groups, if here we had just male and female, if we have more than two groups, then we have to use the ANOVA, analysis of variance test. Before we explore the data, we have to go for the outliers and all that. So we have to talk about whether the normality is satisfied, whether the homogeneity is satisfied, etc. And then we have to correct for the normality, and then we run the ANOVA. If the Levene's test is significant, then we do this post hoc test, either the Welch or Brown force it or the post hoc test, and then we calculate the effect sizes as well. So if we have to show the effect is different across various groups, it could be across various income groups, could be across various regional groups or whatever. When we have more than 2 groups and we want to find out about them, then we do the ANOVA test. So we can do the t-test, we can do the paired samples. What is paired sample? Paired sample means the same person is being tested, maybe before administering them to maybe some violent program or whatever, and once after. So this is a paired sample test. Non-parametric test, I'll just talk about, the Mann-Whitney and the Wilcoxon signed rank and Kruskal-Wallis. These are very simple tests, but basically, where the parametric assumptions are not satisfied, where and even the variables, they may not be interval, they can be ordinal or even categorical. So non-parametric tests, they are random independent samples. We go for the Mann-Whitney test when the 2 samples have have the same shape. So this is one of the assumptions. The Wilcoxon signed rank test, it assumes symmetric distribution. We don't have to go into details about that. So non-parametrics are more conservative. They have less statistical power, and they are more likely than parametric tests to produce type 2 error. What is type 2 error? False negative. What is false negative? Means we are accepting the null hypothesis when actually the null hypothesis is wrong. So non-parametrics have certain issues with them. If you have a non-parametric case for t-test, I just told you t-test, we are trying to find out the difference in whether the difference in means are significant. So when we have a non-parametric analogous test, we go for the Mann-Whitney test. The paired samples t-test is a parametric test. A similar test for non-parametric would be Wilcoxon signed rank. So we give them ranks, and their signed means they are either positive or negative, and then we do it's basically related to the observed frequency and the expected frequency, something like that. The one-way ANOVA, the analogous test is the Kruskal-Wallis test. The one-way repeated measures ANOVA, it's the Friedman's ANOVA. So these are very important non-parametric tests to remember. Chi-square, it either finds out association between 2 or more categorical variables. So it could be between men and women. So who likes cats more, or who likes dogs more, or whatever, and you have those frequencies, and we test whether there is whether there is independent or whether they are very different from each other. So chi-test, it's between categorical variables, and it cannot provide any inference about causation. So the chi-square test is a number that tells you how much difference exists between the observed counts and the count you would expect if there were no relationship at all in the population. Of course, degrees of freedom is very important. So if you have 5 variables, the degree of freedom would be 4. Or if you have it, in rows and columns, so rows -1, columns -1, you multiply that. That is the degrees of freedom. Alpha value, we have already said that it has to be around 0.05 or 0.01. So that's all, about that's all I have to, that's all about today's. Can you hear me? Thank you very much for the opportunity. So that's all I had to share with you all. Thank you very much. Thanks a lot.